The birth of our solar system is a tale written in fire, dust, and unimaginable time. It began long before Earth formed its first ocean, long before the sun blazed its first ray of light, long before atoms that now make up your body ever existed. This story starts in silence. A silence so deep and ancient that it fills the mind with a kind of cosmic awe. Picture a dark stretch of the Milky Way, one spiral arm out of many, quietly drifting through space. In that darkness hangs a massive cloud of gas and dust, cold, quiet, and unremarkable. Astronomers call it a molecular cloud. It doesn't look like the birthplace of anything extraordinary. It is dim, almost hollow, a drifting shadow in the galaxy, made of hydrogen, helium, and tiny grains of carbon and silicates. And yet, inside that cloud lies the raw material of everything we know. For millions of years, this cloud remains still. Nothing changes. Nothing stirs. But the universe is never perfectly quiet. A nearby star reaches the end of its life and collapses, then explodes in a supernova. The blast is violent. It sends a shock wave racing through the galaxy, sweeping across the molecular cloud with incredible force. And in that moment, everything shifts. The shock wave compresses the cloud. Pressure builds. Gravity begins to tighten its grip. What was once a calm sea of particles becomes a swirling, collapsing mass. A cosmic domino effect has begun, and there is no turning back. This is the true beginning of our solar system. At the center of the collapsing cloud, matter piles inward. Gas gathers. Dust spirals. And gravity, always the sculptor of worlds, begins to carve the future sun. As the material compresses, it heats up. At first, the warmth is faint, barely a whisper, but slowly it grows. The center glows. The glow becomes a burn. The burn becomes a furnace. And inside that growing sphere of fire, nuclear fusion is waiting to ignite. Around this forming sun, the rest of the cloud flattens into a vast, spinning disk. This disk stretches billions of miles across. It is thin, elegant, and full of potential. Scientists call it the protoplanetary disk, and it is the workshop where all future planets are forged. Every grain of dust inside it is a building block. Every swirl of gas is a note in the coming symphony of creation. But this place is not peaceful. Far from it. The early solar system is violent, chaotic, raw. Imagine a storm of rock and ice, pieces ranging from microscopic specks to mountain-sized boulders, colliding at tremendous speeds. Each collision releases heat. Each impact changes the shape of the disk. The swirling material sticks together, breaks apart, sticks again, and gradually begins to form larger and larger bodies. These are the planetesimals, the seeds of planets. They start small, but with each collision, they grow. Some reach the size of houses. Some become the size of cities. And, over millions of years, a few of them grow large enough to influence everything around them. Gravity becomes their tool. Mass becomes their advantage. The biggest planetesimals vacuum up surrounding material, clearing paths and shaping orbits. In the inner part of the disk, where temperatures are high, only metal and rock can survive. This is where Mercury, Venus, Earth, and Mars will eventually form. Farther out, where it is cold enough for ice to exist, hydrogen and helium remain intact. This is the territory of giants Jupiter, Saturn, Uranus, and Neptune. Each will come to dominate its own region, sculpting the future architecture of the solar system. But for now, in this first chapter of cosmic creation, nothing resembles the planets we know. Everything is in motion. Everything is changing. Dust becomes rock. Rock becomes boulders. Boulders become worlds. And in the center, the sun is still gathering power. As the young sun grows denser and hotter, pressure builds in its core to an extreme level. Hydrogen atoms are squeezed together so tightly that they begin to fuse into helium. And in a single moment, one of the most important moments in cosmic history, the sun is born. Light bursts outward. Solar winds roar across the disk, pushing the remaining gas and dust outward. The era of formation is over. The era of shaping has begun. With the sun's ignition, the rules inside the solar system change. The solar wind clears the inner disk of gas, allowing rocky planets to continue forming without interference. Farther out, the gas giants absorb enormous amounts of hydrogen and helium before the expanding wind sweeps the rest away. The early solar system becomes a construction site. Thousands of young worlds crash into each other, merge, or shatter entirely. Some are absorbed into larger bodies. Some are flung into deep space. Some spiral into the sun and vanish forever. Chaos does not mean disorder. It is simply the universe's way of choosing what will survive. Among these countless collisions, one world begins to take shape, a world destined to become our home. It starts as a small, molten sphere of rock. It absorbs other planetesimals, growing larger and hotter with every impact. A Mars-sized object slams into it, blasting debris into space. From that debris, our moon will one day form. Earth stabilizes. The crust cools. Oceans eventually appear. But all of this lies far ahead. At this early stage, Earth is just one young planet among many. To its left and right, new worlds are forming, some destined to remain, others doomed to disappear. Jupiter is growing into a monster, pulling in massive amounts of gas and developing a gravity well so powerful that it shapes the fates of every planet inward from its orbit. The solar system settles. Orbits stabilize. The chaos begins to fade. What remains are the early versions of the planets we know. A blazing sun at the center, rocky inner worlds, gas giants beyond, and a cloud of icy objects stretching outward into the dark. This is the birth of our solar system, a story that took millions of years to play out, yet shaped every detail of the night sky we see today. It is a story written in heat, gravity, and motion. A story that begins in darkness but ends in light. And as we move into the next chapter, explore how this newborn system evolved, how planets acquired their identities, and how the chaos of creation slowly transformed into the ordered harmony we live in now. The story of our solar system continues with a moment of transformation so dramatic that it changed the fate of an entire region of the galaxy. To understand how everything unfolded, we need to return to that ancient molecular cloud, the cold, drifting giant made of gas and dust just before the collapse began. At first glance, it seemed completely still. For millions of years, the cloud hung quietly in the Milky Way, untouched and undisturbed, a dark reservoir of raw material waiting for something to happen. But deep inside, the balance was delicate. Gravity pulled inward. Pressure pushed outward. Any disturbance could tip the scales. The disturbance arrived in the form of a supernova, A star not far from the cloud reached the end of its life and exploded with an intensity so overwhelming that it flooded nearby space with energy. The blast raced outward at thousands of miles per second, carrying shockwaves through the galaxy. When one of those shockwaves slammed into the molecular cloud, everything changed. The cloud buckled, it compressed, and, in that instant, gravity gained the upper hand. What had once been a diffuse, ghost-like cloud began to collapse inward. Gravity acted like a giant hand, gathering material from all directions. As the collapse continued, denser regions formed within the cloud. These pockets of higher density, called clumps, became the seeds of stars. One of those clumps would eventually become the sun. At this stage, nothing resembled the brilliant star we know today. The material was still cold and dark, but the collapse had set in motion a chain of events that could no longer be stopped. The cloud was shrinking, spinning, heating, and evolving moment by moment. As the clump destined to become the sun continued collapsing, it began to rotate. This rotation wasn't random. It came from a subtle twist in the cloud's original motion. But as the clump contracted, the rotation increased, much like a figure skater spinning faster when pulling their arms inward. The faster spin flattened the collapsing material into a vast disk. The center grew dense and hot, while the surrounding material formed a thin, swirling structure stretching billions of miles across. This was the protoplanetary disk, the cradle of the future solar system. Inside this disk, temperatures varied dramatically. Near the center, heat from the forming sun was intense, hot enough to vaporize most materials. Farther out, temperatures dropped sharply, allowing ice, carbon compounds, and gas to remain intact. These temperature differences would shape the identities of the future planets. The inner worlds would become rocky. The outer worlds would become gas giants. But in this early moment, none of that existed yet. Everything was still dust, gas, and turbulence. Meanwhile, the center of the collapsing clump continued to evolve. As more material fell inward, pressure at the core increased. Temperature climbed. The forming sun, still just a protostar, glowed faintly, not from fusion, but from the sheer heat of gravitational compression. If you could have seen it then, it would not look like our sun. It would resemble a dim, swollen ball of hot gas wrapped in a rotating shroud of dust. But it was changing quickly. The protostar pulled more and more material toward itself. Streams of gas spiraled inward. Jets of energized particles blasted outward from its poles, clearing paths through the disk. These jets were powerful enough to reshape the surrounding region, carving cavities into the cloud. They also signaled something important. The protostar was in its final stages of formation. It was almost ready to ignite. While the young sun transformed at the center, the disk around it became a dynamic arena of collisions. Dust grains stuck together through static forces. Tiny clumps grew into pebbles. Pebbles grew into rocks. Rocks grew into boulders. And each time they collided, they either bonded or shattered. This process played out millions of times over millions of years. It was slow, chaotic, and relentless. Some regions of the disk became unusually dense, forming swirling vortices. These vortices acted like traps, pulling in material and concentrating it. Inside them, planetesimals, small bodies that served as the building blocks of planets, began to form. Some were only a few miles wide. Others reached hundreds of miles across. These young planetesimals resembled rough, irregular pieces of stone drifting through a storm of dust. But in time, a few would grow large enough to dominate their surroundings. The inner disk was especially violent. The high temperatures meant only metals and rocks survived. This region became the birthplace of Mercury, Venus, Earth, and Mars. Each began as clusters of planetesimals colliding and merging. The young inner worlds were molten, unstable, and hungry for mass. Every impact changed their shape. Every collision added heat. These early collisions wouldn't have looked anything like meteor impacts today. They were catastrophic, world-shaping events that generated enough energy to melt entire surfaces. Farther out, conditions were different. Temperatures were low enough for ice to remain solid. This allowed planetesimals in the outer disk to grow much larger, much faster. Ice was abundant and easy to accumulate. And ice brought mass. With mass came gravity. And with gravity came the ability to attract enormous amounts of hydrogen and helium, the lightest elements in the universe. These outer planetesimals became the cores of Jupiter, Saturn, Uranus, and Neptune. Within only a few million years, they grew into giants. All of this was happening while the sun's core approached the threshold needed for nuclear fusion. Pressure built layer by layer. Hydrogen atoms were forced closer and closer together. When the density reached a critical point, hydrogen began fusing into helium. This reaction released tremendous energy. And in a single, defining moment, the sun was born. It lit up with a brilliance that swept outward through the disk. Light radiated. Heat surged. Solar winds blasted through the remaining gas. The environment changed instantly. The ignition of the sun marked a turning point. It ended the era of collapse and began the era of architecture. The solar wind pushed the lighter materials outward, clearing the inner disk of gas and leaving only dust and rock behind. This ensured that the inner planets stayed small and rocky. The outer planets, having already gathered thick envelopes of gas, retained their massive atmospheres. The solar system's layout was beginning to form. But even after the sun ignited, the chaos was far from over. The protoplanetary disk continued to evolve. Orbits shifted. Collisions intensified. Some planetesimals merged to become planets. Others were ejected into distant space. Some spiraled into the sun and vanished. The early solar system was a battlefield of gravity and motion, a place where only the most stable worlds survived. And yet, from this violence came order. The planets found their orbits. The disk thinned. The last remaining gas dissipated. What began as a silent cloud of dust had now transformed into a young solar system brilliant at the center, turbulent around the edges, and full of worlds still shaping their identities. The young solar system was no longer a silent cloud drifting through space. It had become a spinning disk of fire, dust, and relentless motion. At the center, the newborn sun burned with fresh intensity. Its light cut through the darkness. Its heat reshaped the surrounding gas, and its gravity anchored everything around it. But beyond that bright center, stretching billions of miles in every direction, the protoplanetary disk churned like a cosmic storm. Imagine standing inside this vast disk, though no human could ever survive its heat, dust, or violent collisions. The view would be overwhelming. Fine particles of rock drifted like smoke. Larger fragments tumbled through space, glowing faintly from the friction of constant impact. Rivers of gas swirled in long, elegant arcs. And everywhere, gravity was playing its ancient game, pulling, pushing, and sculpting the future of every world that would one day exist. The inner regions of the disk were scorching hot. Temperatures climbed high enough to melt most materials. Here, only metals and silicate rocks could survive. This harsh environment set the stage for the birth of the 4 terrestrial planets: Mercury, Venus, Earth, and Mars. But none of these worlds existed yet. What filled this region instead was a dense sea of debris, countless planetesimals smashing, merging, and breaking apart. Each collision released bursts of energy. Some events were small, like 2 pebbles tapping against each other. Others were catastrophic, powerful enough to vaporize entire bodies. This was the process that built planets from the ground up. Through millions of impacts, small fragments grew larger. Larger fragments grew into boulders. Boulders became mountain-sized objects. And in time, the largest planetesimals became protoplanets, early versions of the planets we know today. These protoplanets were far from stable. They wandered through the disk on shifting orbits, interacting with every piece of material around them. One protoplanet might grow by absorbing dozens of smaller bodies in a single week. Another might be shattered by a violent collision, scattering its fragments back into the disk. The boundaries between construction and destruction blurred. Growth came at a cost. Nothing became large without earning it. Farther from the sun, conditions were different. The temperature dropped sharply, allowing ices and frozen gases to remain solid. Water ice, methane ice, carbon dioxide ice, all of them existed in abundance. And because these materials were less dense but far more plentiful than rock, the planetesimals in this region grew quickly. The outer disk became a breeding ground for giant planetary cores. The seeds of Jupiter and Saturn formed first. Their cores, made of heavy elements and ices, grew to several times the mass of Earth. Once they reached a critical size, their gravity became strong enough to pull in enormous quantities of hydrogen and helium from the surrounding disk. These gases spiraled inward, enveloping the cores in vast, expanding atmospheres. Within a relatively short period of time, Jupiter became the titan of the solar system. But Jupiter's growth came with consequences. Its massive gravity created waves in the disk, much like a ship moving through water. These waves altered the orbits of nearby planetesimals, often pushing them inward or outward. Some were ejected entirely. Others collided with growing planets in the inner disk. Jupiter's influence reshaped the architecture of the solar system long before the planets were fully formed. Saturn followed, developing its own massive envelope of hydrogen and helium. Though smaller than Jupiter, it still commanded incredible gravitational power. Together, these 2 gas giants dominated the outer regions, carving paths through the disk and dictating the motion of everything around them. Even farther out, in the coldest reaches of the disk, the cores of Uranus and Neptune began to form. They gathered ices and small amounts of gas, but by the time they grew large enough to attract more hydrogen and helium, the sun's powerful solar wind had already begun blowing the remaining gas out of the disk. As a result, Uranus and Neptune remained ice giants rather than true gas giants. While the outer worlds grew, the inner disk continued its chaotic evolution. Protoplanets collided with one another repeatedly. Each collision redefined the shape of the young solar system. Some collisions were glancing blows, stripping away crust or altering orbits. Others were head-on impacts, powerful enough to reshape entire worlds. The early Earth, for example, experienced dozens of catastrophic collisions long before it settled into anything resembling stability. The most famous of these collisions involved a Mars-sized protoplanet, often called Theia. It struck the young Earth in a catastrophic, world-changing impact. The collision melted Earth's surface and ejected an enormous amount of debris into space. Over time, this debris coalesced into a single, stable body, the Moon. But this dramatic chapter belongs later in our story. For now, Earth was still one of many worlds fighting to survive the violence of the disk. As millions of years passed, the protoplanetary disk slowly thinned. Much of the gas had been pulled into the sun or absorbed by the gas giants. Dust and rock had merged into larger bodies. The number of collisions decreased, but they did not stop. Even in this later stage, the solar system was far more violent than anything we can imagine today. During this period, the orbits of the growing planets began to stabilize. Jupiter settled into its massive, commanding orbit. Saturn found its place beyond it. Uranus and Neptune drifted outward as gravitational interactions pushed them to their modern positions. The inner planets began carving their own orbits from the remaining debris, though they were still small and molten. This was the moment when the architecture of the solar system took shape. Not perfectly, not permanently, but clearly enough that the basic structure we know today was already forming. The Sun at the center. 4 rocky planets inside. 4 giant planets outside. And beyond them, a vast population of icy bodies stretching into the distant dark. But the story was far from complete. The worlds were young. Many were still molten. Their atmospheres were unstable. Their surfaces changed rapidly, and collisions, though less frequent, continued to sculpt them. The disk itself continued to thin until only traces remained. What had once been a massive, the swirling structure of gas and dust slowly faded into the quiet emptiness of space. But its legacy remained in the planets, moons, asteroids, and comets that now filled the solar system. The inner solar system was once a place nothing like the calm, predictable environment we know today. In the era just after the sun ignited, the space near it was violent, molten, and relentless. Temperatures soared. Debris moved at incredible speeds, and the future rocky planets Mercury, Venus, Earth, and Mars were only beginning their long struggle toward stability. To understand how these 4 worlds took shape, we need to step inside that brutal environment and watch as heat, gravity, and collision sculpted them into existence. The first thing to understand is that the inner region of the protoplanetary disk was extremely hot. So hot, in fact, that volatile materials like water, methane, and ammonia couldn't survive in solid form. The only substances capable of enduring the intense heat were metals and silicate rocks. This simple fact determined everything that followed. It meant the inner planets would be small, dense, and rocky. It meant they would lack thick gaseous shells like those of the giants farther out. And it meant their early surfaces would be shaped by fire. As the disk evolved, the dense cloud of debris circling the young sun began to thin. But for millions of years, the inner region remained packed with countless planetesimals. These planetesimals collided constantly. Some grew, some shattered, some spiraled inward and vanished into the sun. The survivors, those that managed to grow faster than they were destroyed, became the seeds of the future planets. One of the earliest of these emerging worlds was Mercury. Positioned closest to the sun, Mercury formed in the hottest region of the inner disk. There, intense radiation blasted away anything light enough to escape. As a result, the early Mercury became an incredibly dense world. Its iron core grew disproportionately large, while its outer layers remained thin. Early on, the planet was molten, glowing with the heat of ongoing impacts. Occasionally, large collisions stripped away parts of its surface, leaving it even smaller than it might otherwise have become. The Mercury we see today, with its massive core and thin mantle, is a direct product of that brutal early history. Farther out, Venus took shape in a region slightly cooler than Mercury's orbit, yet still dominated by intense heat. Venus grew efficiently, absorbing planetesimals at a rapid pace. Its size increased steadily, allowing its gravity to strengthen. But Venus' early environment was no gentler. Its surface was a hellish ocean of magma. Impacts continued to rain down, reshaping it again and again. And even after the collisions slowed, Venus retained a thick atmosphere of carbon dioxide and nitrogen, an atmosphere that would one day evolve into the crushing, toxic cloud layer we know today. But in these early stages, Venus was simply a massive, molten world searching for equilibrium. Earth formed just beyond Venus, in a region where temperatures were slightly lower but still high enough to keep the surface molten for millions of years. Earth's formation came through countless collisions with objects both small and enormous. Each impact delivered heat. Each collision added mass. And with every new addition, the young Earth grew stronger. Its core differentiated early, separating into layers of iron and nickel in the center and lighter silicates above. This process created a powerful magnetic field that would later become one of Earth's greatest defenses against solar radiation. But Earth's road to stability was marked by one collision more important than all the others. A Mars-sized protoplanet, known as Theia, struck Earth in a catastrophic impact. The collision ejected enormous amounts of molten rock into space. Over time, this debris formed a ring around Earth. And from that ring, the Moon gradually emerged. The presence of the Moon would eventually stabilize Earth's rotation, shape its tides, and play a crucial role in the evolution of life. But in this early moment, Earth was still a molten world recovering from an impact that nearly destroyed it. Beyond Earth, Mars formed in a region where the density of material began to decrease. Because there was less debris available, Mars grew more slowly and remained smaller than Earth or Venus. Its early molten surface cooled faster. Its gravity was weaker, and its ability to retain heat and atmosphere was limited from the start. Mars might have become a larger, more Earth-like planet, if not for the powerful gravitational influence of Jupiter. The giant's presence disrupted Mars' growth, scattering material before the young world could absorb it. As a result, Mars ended up as a smaller, colder, and more fragile planet, a world forever marked by what it could have been. During this era, the inner planets were shaped by a phenomenon known as differentiation. As each world grew, its interior heated to the point where heavier elements sank to the center, while lighter materials rose to the surface. This created cores, mantles, and crusts. It set the stage for volcanic activity. It determined magnetic fields, and it ultimately defined the long-term evolution of each planet. Even as the planets formed their basic structures, they remained far from stable. Molten oceans covered their surfaces. Atmospheres were thick with sulfur, carbon dioxide, and vaporized minerals. The skies were filled with debris from constant impacts, and temperatures rose and fell depending on the intensity of the collisions. Life, if we imagine it, would have had no chance to survive here. Everything was in motion. Everything was unstable. Eventually, however, the era of giant impacts began to slow. The inner solar system gradually cleared as the planets absorbed or expelled the remaining debris. Orbits stabilized. Surfaces cooled. Crusts solidified. Environments began to diverge. Venus retained a thick, suffocating atmosphere that trapped heat and created a runaway greenhouse effect. Earth cooled enough for water vapor to condense, forming its first oceans. Mars cooled too quickly, losing much of its early atmosphere and volcanic heat. The inner planets, though neighbors, became drastically different worlds, one scorching, one vibrant, one frozen. Yet all of them shared a common origin, the fire and fury of the early disk. By the end of this era, the architecture of the inner solar system was nearly complete. The planets had taken shape. Their orbits were stable. The worst of the impacts had ended, and the debris that once choked the region began to fade into the background, leaving behind a cleaner sky and a calmer environment. While the inner planets were fighting their way through a storm of molten rock and constant impacts, a very different drama was unfolding in the outer solar system. Out beyond the region where heat from the sun could melt rock or metal, a colder environment took shape, an environment where ice, gas, and dust gathered to form worlds on a completely different scale. These worlds would become the giants: Jupiter, Saturn, Uranus, and Neptune. Their birth was not just a story of growth, it was a story of domination. Their emergence would shape the entire structure of the solar system and determine the fate of every other planet. The outer solar system began with an enormous advantage: temperature. Far from the sun, the protoplanetary disk was cool enough for ice's water, methane, carbon dioxide, ammonia to remain solid. These ices were not only abundant but lightweight, easy to capture, and perfect for building massive cores. While the inner planets had to grow slowly from dense, limited rock and metal, the outer planets had access to a much larger supply of raw material. This difference set the giants on a path of rapid growth. Within a few million years, planetesimals in the outer disk collided and merged at a pace far faster than in the inner system. They formed icy bodies the size of mountains, then continents, then entire worlds. As these icy bodies grew, their gravity increased. And once a protoplanet reached several times the mass of Earth, it crossed a critical threshold. Its gravity became strong enough to pull in hydrogen and helium, the lightest, most abundant elements in the universe. This moment marked a turning point. The outer world didn't just grow. It ballooned. It transformed. It became something the inner planets could never become: a gas giant. Jupiter was the first to reach this milestone. Its core, built from a mixture of rock and ices, grew swiftly to a mass estimated at 10 times that of Earth. Once it crossed that threshold, Jupiter began absorbing hydrogen and helium from the surrounding disk. Gas streamed toward it in long, spiraling currents. Its atmosphere expanded. Its gravity intensified. And in a relatively short period of time, Jupiter became a world of staggering proportions. It wasn't just bigger than the inner planets. It was in a league of its own. As Jupiter grew, it began reshaping its surroundings. Its massive gravity generated waves within the disk, much like ripples in water. These waves displaced smaller bodies, altering their orbits or ejecting them entirely. Jupiter became the great sculptor of the solar system. Some planetesimals it pushed inward, contributing to the bombardment of the inner worlds. Others it hurled outward, sending them into deep space. Without Jupiter, The inner planets might have grown larger. Mars might have become Earth-like. The asteroid belt might have formed a planet. But Jupiter's rise ensured that none of these outcomes would happen. Next came Saturn. Forming slightly farther from the Sun, Saturn grew more slowly, but it followed the same pattern as Jupiter. A heavy core, a rapid accumulation of hydrogen and helium, a dramatic expansion into a giant. Saturn never reached Jupiter's immense mass, but it still became a world of extraordinary scale, wrapped in thick bands of gas and swirling storms. Together, Jupiter and Saturn created a gravitational partnership that dominated the outer solar system. Their combined influence shaped orbits billions of miles away. They controlled the flow of material. They carved out gaps in the disk. They created resonances repeating gravitational rhythms that either stabilized or disrupted the paths of smaller bodies. Their presence was felt everywhere. Farther out, in the cold, distant reaches of the disk, two more giants were forming, but with a different fate. Uranus and Neptune began as icy cores like Jupiter and Saturn, but the timing of their growth worked against them. By the time they reached the size needed to attract significant amounts of hydrogen and helium, the Sun had already ignited. Its solar wind streams of charged particles blasting outward was clearing the remaining gas from the protoplanetary disk. The window for becoming gas giants was closing fast. As a result, Uranus and Neptune gathered thick atmospheres, but not nearly as much hydrogen and helium as Jupiter or Saturn. They remained smaller, denser, and less dominated by gas. Today, we call them ice giants, a category distinct from the gas giants. Their atmospheres contain hydrogen and helium, but also large amounts of methane and ammonia. Their interiors are composed of water-rich ices crushed under enormous pressure. They are colder, darker, and more mysterious than their larger siblings closer to the Sun. Yet even with their differences, all four giants shared one role. They controlled the architecture of the outer solar system. Jupiter especially became a gravitational gatekeeper. When smaller objects drifted inward, Jupiter often flung them away before they could reach the inner planets. When comets formed in the outer regions, Jupiter shepherded many of them into long ellipses or sent them into interstellar space. Saturn, Uranus, and Neptune added their own influences, shaping belts of icy objects into stable orbits that still exist today. The outer planets also moved. As Jupiter and Saturn interacted with the disk, they migrated slightly inward and outward. These migrations caused resonances that scattered countless icy planetesimals. Some were pushed into the region beyond Neptune, forming what would become the Kuiper Belt. Others were ejected into the distant reaches of the Sun's gravitational influence, creating a vast spherical cloud of frozen bodies that today we call the Oort cloud. These migrations were not simple. They occurred over millions of years and involved complex gravitational dances between the giants. But the result was clear. The giants didn't just form in the outer solar system. They shaped it. They defined it. They preserved it. Meanwhile, the inner planets continued cooling and stabilizing. With Jupiter clearing much of the inward flowing debris, the frequency of catastrophic impacts gradually declined. Earth's crust began to solidify. Venus' atmosphere thickened. Mars' interior cooled. Mercury's thin mantle settled. And slowly, the solar system transitioned from chaos to order. Planets settled into long-term orbits. Moons formed and stabilized. Asteroid belts and icy regions found their boundaries. The protoplanetary disk, once the turbulent birthplace of every world, continued to thin until it faded into near nothingness. By the time the giants reached their final forms, the solar system was no longer a place of constant collisions and molten oceans. It had become a structured, multi-layered system filled with worlds of every size and composition. At the center, a shining star. Around it, rocky planets. Beyond them, two gas giants. And farther still, two ice giants. Together, they formed a dynamic, interconnected family, a system that would endure for billions of years. With the planets formed and the protoplanetary disk fading into silence, the solar system entered a new phase 1, defined not by violent collisions, but by the slow, powerful process of cooling. After millions of years of blazing heat, molten oceans, and glowing surfaces, the young worlds finally began to settle. Their crusts thickened, their atmospheres shifted, their identities emerged. This transformation would shape the landscapes, climates, and destinies of all 8 planets. The story of cooling is, at its heart, a story of balance. When the planets first formed, their surfaces burned with leftover heat from accretion. Every impact, every merger, every fragment that fell onto their surfaces added energy. Many young worlds were so hot that their surfaces glowed red. Their crusts churned like the surface of a lava lake. But over time, heat radiated into space. Slowly, relentlessly, the planets began to cool. Mercury cooled first. Being small and close to the sun, it lost internal heat quickly. The planet shrank as its interior contracted, forming enormous cliffs known as lobate scarps. These cliffs stretched for hundreds of miles, rising like frozen waves on a silent ocean of rock. Mercury's thin crust hardened early, its volcanic activity waned, and the planet froze into a world defined by extremes, scorching days, freezing nights, and a landscape etched by ancient impacts. Venus cooled more slowly. Its larger size trapped heat for much longer. Early on, the planet's surface was a vast sea of molten rock. Volcanic activity was intense. Gases escaped into the atmosphere, creating a thick blanket of carbon dioxide. As Venus cooled, its surface hardened, but its atmosphere remained dense. Over time, the thick CO2 trapped heat so effectively that the planet experienced a runaway greenhouse effect. Temperatures soared high enough to melt lead. Clouds of sulfuric acid formed. The surface became a pressure cooker, crushing anything that descended to its rocky plains. Cooling did not bring stability to Venus. It brought a permanent transformation into one of the most hostile environments in the solar system. Earth followed its own unique path. As its surface cooled, water vapor condensed into clouds. Torrential rains fell for millions of years, collecting into enormous oceans that covered much of the planet. Volcanoes continued erupting, releasing gases that formed a young atmosphere. But Earth had 2 powerful advantages: a strong magnetic field and a stable moon. The magnetic field protected the early atmosphere from the sun's harsh solar wind. The moon stabilized Earth's axial tilt, preventing chaotic climate swings. Together, these features gave Earth something rare in the solar system: long-term environmental stability. As the crust thickened, Earth's interior remained warm enough to drive plate tectonics. These shifting plates created mountains, ocean basins, volcanic islands, and continents. Even in this era of cooling, Earth was dynamic, its surface constantly reshaped by forces beneath it. In time, these geological processes would create environments capable of hosting life. But life would still take millions of years to appear. For now, Earth stood as a cooling, stabilizing world with oceans, atmosphere, and a surface beginning to take its permanent shape. Mars cooled quickly. Smaller than Earth and farther from the Sun, Mars lost internal heat at a rapid pace. Early in its history, Mars likely had a thick atmosphere, flowing rivers, and large lakes. Volcanoes like Olympus Mons, the largest in the solar system, erupted frequently, reshaping the landscape. But as the planet cooled, its core weakened. The magnetic field faded. Without magnetic protection, the solar winds stripped away much of the atmosphere. Water evaporated into space. Temperatures dropped. Rivers froze or disappeared. Mars became a cold, barren desert with the echoes of a warmer past etched into its valleys. While the inner planets cooled, the giants underwent their own transformations. Jupiter, already a massive world of gas and storms, generated heat not from sunlight but from its own internal processes. As Jupiter contracted under its own gravity, it released energy. This contraction is still ongoing. The planet radiates more heat than it receives, fueling storms that rage for centuries. The famous Great Red Spot, a storm larger than Earth, may have begun forming during this very era of cooling. Saturn underwent a similar process, contracting slowly and radiating heat from its interior. But Saturn developed a unique signature, the formation of early ring structures. These early rings were not the spectacular, icy bands we see today, but temporary features created by the breakup of moons or captured debris. As the planet cooled, its thick atmosphere developed layered clouds and powerful jet streams. Uranus and Neptune, much colder and smaller than their inner siblings, cooled in quieter ways. Their atmospheres stabilized into mixtures of hydrogen, helium, and methane, the methane giving both planets their blue colors. Deep below their clouds, layers of water, ammonia, and methane existed in forms we cannot easily imagine. Superheated ices, crushed under enormous pressure, flowing like slush or liquid metal. These ice giants remained cold, distant, and stable, their cooling processes slow but steady. As the planets transformed, the space between them changed as well. The asteroid belt formed from leftover debris that never grew into a planet began to stabilize. Jupiter's gravity prevented accretion, ensuring the belt remained a region of scattered bodies. Some were large enough to differentiate into cores and mantles. Others remained primitive, unchanged since the birth of the solar system. These asteroids became time capsules, preserving clues about conditions billions of years ago. Beyond Neptune, the Kuiper Belt took shape, a distant zone of icy bodies, dwarf planets, and frozen debris. Objects like Pluto, Eris, and Haumea formed here, each with unique compositions and histories. These icy worlds cooled into frozen spheres, locked in distant orbits that barely changed for billions of years. Their surfaces became records of the solar system's earliest days. Cooling also influenced the birth of moons. Many moons formed when material left over from planetary creation coalesced into smaller bodies. Others were captured objects, asteroids, or icy planetesimals pulled into orbit by a planet's growing gravity. Some moons remained geologically active, heated by tidal forces. Others cooled into silent, cratered worlds. Across the solar system, cooling brought stability. It marked the end of the violent, molten era and the beginning of long-term evolution. But it did not erase the scars of the past. Every crater, every ridge, Every valley carved into the planets and moons told a story of what came before. By the time the planets fully cooled and stabilized, the solar system looked remarkably similar to what we see today. The sun shone steadily. The planets orbited in predictable paths. The debris that once filled space had mostly been cleared or absorbed. And a new kind of era was beginning, an era where the conditions for habitability emerged on one planet in particular. Even after the planets cooled and the early chaos faded, the solar system was not yet a peaceful place. A new storm was approaching, a storm unlike anything before or since. For a period lasting hundreds of millions of years, a relentless cascade of asteroids, comets, and rocky debris swept through the inner planets, pounding their surfaces with devastating force. This period is known as the Late Heavy Bombardment. It was a cosmic rain of fire. It reshaped the landscapes of Mercury, Venus, Earth, and Mars. And it left scars still visible today. To understand why the bombardment happened, we need to revisit the giant planets. Jupiter and Saturn, with their enormous gravity, were not fixed in place when they first formed. They migrated, shifting inward and outward as they interacted with the remaining gas and debris in the protoplanetary disk. These migrations did more than nudge the planets into new positions. They set off a chain reaction throughout the solar system. As Jupiter and Saturn crossed certain orbital resonances, their combined gravity destabilized vast regions of space. Objects in the asteroid belt were thrown into chaotic paths. Comets in the outer regions were flung inward. Moons experienced gravitational jolts. And millions of icy and rocky bodies, which had quietly orbited for hundreds of millions of years, were suddenly sent hurtling toward the inner solar system. This was the beginning of the bombardment. The inner planets were now in the path of a storm of cosmic debris. Every world, Mercury, Venus, Earth, and Mars was battered by an extraordinary number of impacts. Some of these collisions were small, leaving craters only a few miles wide. Others were catastrophic, forming basins hundreds of miles across. The Moon, which has no atmosphere to erode or hide its scars, remains the best record of this era. Its surface is covered with craters that formed during this intense bombardment, including some of the largest impact basins in the solar system. On Mercury, the bombardment carved massive craters and basins into its already cooling surface. The planet's thin crust cracked under the repeated impacts, producing long cliffs and ridges as the world continued to shrink and settle. Mercury's surface today is a museum of this violent period, each crater a fossil of an ancient collision. Venus, wrapped in a thick atmosphere, hides most of its ancient scars. Over time, volcanic activity resurfaced the planet, covering older impacts. But during the bombardment, Venus endured the same barrage of collisions as its neighbors. Many of those early craters were buried under lava flows or erased by geologic processes. Even so, radar imaging shows that Venus still carries the echoes of those ancient impacts beneath its dense clouds. Earth faced impacts unlike anything humanity can easily imagine. Some collisions vaporized oceans. Others melted vast regions of the crust. The atmosphere filled with fire and ash. Yet almost none of these early scars remain today. Earth's active geology, plate tectonics, erosion, weather slowly erased most evidence of the bombardment. But the effects were profound. These massive impacts delivered water, organic molecules, and volatile compounds to the young Earth. They contributed to the formation of oceans, the chemistry of the atmosphere, and the early conditions that would one day allow life to emerge. The moon tells Earth's untold story. Because the moon is geologically quiet, its surface still preserves the craters from the late heavy bombardment. Every crater on the moon older than about 8 billion years is a silent witness to the impacts that also struck Earth, impacts that shaped its continents, its crust, and its future. Mars, too, bears the marks of the bombardment. Vast plains of ancient craters show the violent history of its early surface. The northern hemisphere of Mars contains a giant depression, the Borealis Basin, a structure so large that some scientists believe it may have been formed during this era by a massive impact. The bombardment also delivered water ice to Mars, contributing to what may have once been a warmer, wetter climate. For hundreds of millions of years, the inner solar system endured this relentless storm. The impacts were not random. They followed a pattern driven by gravitational mechanics resonances created by the shifting orbits of the giant planets. And then, slowly, the bombardment faded as the solar system stabilized. Jupiter and Saturn settled into their final orbits. The chaos of scattering objects subsided. Most of the remaining debris was either absorbed by planets, ejected into deep space, or settled into stable regions like the asteroid belt and Kuiper belt. When the bombardment ended, the solar system was forever changed. The planets had been carved, reshaped, and chemically enriched. Their surfaces bore scars that told the story of their survival. Their atmospheres had been altered. Their crusts had been fractured, melted, and rebuilt. And in the case of Earth, something even more significant had occurred. The conditions were now in place for life to begin. The bombardment delivered essential ingredients: water, carbon compounds, amino acids from comets and asteroids. It stirred Earth's oceans, enriched the soil, and provided the chemical complexity necessary for the first biological molecules to form. Far from being merely destructive, the bombardment was also creative. It set the stage for everything that would follow. By the time the late heavy bombardment ended, roughly 8 to 4 billion years ago, the solar system had transitioned into a quieter, more stable era. Planets orbited smoothly. Large impacts became rare. Oceans settled. Atmospheres thickened. And the long, slow evolution of worlds began in earnest. When the fury of the late heavy bombardment finally faded, the solar system entered an era of profound transformation. The planets had survived a storm of impacts powerful enough to melt surfaces, shatter crusts, and reshape entire hemispheres. Now, with the reign of asteroids slowing and gravitational chaos settling into order, each planet began developing its permanent identity. Crusts hardened, atmospheres stabilized, volcanic plains expanded, oceans formed or disappeared, and the landscapes that would endure for billions of years took shape. The young sun shone steadily at the center of it all, no longer fighting to ignite, but now burning with the quiet strength of a star in its prime. Its energy warmed the inner worlds, drove atmospheric currents, and influenced chemical reactions on planetary surfaces. But each planet responded in its own way, shaped by size, composition, distance, gravity, and its own internal heat. Mercury was the first to settle into the world we recognize today. Small, dense, and positioned closest to the sun, Mercury cooled rapidly once the bombardment eased. Its surface became a mosaic of ancient craters, frozen lava plains, and enormous cliffs created when the entire planet shrank. The bombardment had carved deep basins, including the massive Caloris Basin, one of the largest and most dramatic impact structures in the solar system. Mercury's thin atmosphere, barely more than a whisper, could not protect it from further impacts, nor could it trap heat. Daytime temperatures soared. Nighttime temperatures plummeted. The planet became a world of extremes, scarred but stable, silent yet enduring. Venus, meanwhile, evolved along a completely different path. Early in its history, Venus may have had shallow oceans and a more Earth-like environment. But as the bombardment ended, volcanic activity surged across the surface. Thousands of volcanoes erupted, releasing enormous quantities of carbon dioxide into the atmosphere. Without oceans to absorb it, the CO2 accumulated. As the atmosphere thickened, surface temperatures rose. The warming caused more volcanic release, which triggered even more warming, a runaway greenhouse effect. By the time the cycle stabilized, Venus had transformed into an inferno, its surface baked under crushing atmospheric pressure. Clouds of sulfuric acid swirled above. The bombardment played only a small role in this transformation. But the cooling period afterward allowed the planet's volcanic personality to take over completely. Earth's story was more balanced. After the bombardment, Earth retained enough heat to sustain active geology, but cooled enough for water vapor to condense into oceans. Rain fell for millions of years, carving early valleys and filling vast basins. Lightning flashed. Volcanoes erupted. Tectonic plates began shifting, creating young continents. The atmosphere, once thick with volcanic gases, began evolving into a mixture capable of supporting future life. This was a time of extraordinary chemical transformation. Energy from the sun, the oceans, and the planet's interior encouraged reactions that produced increasingly complex molecules. Earth stabilized into a world of water, rock, and air. Its crust thickened. Its climate found equilibrium. And slowly, the first hints of habitability emerged. Mars cooled much faster than Earth, and its transformation was dramatic. During the bombardment, Mars had rivers, lakes, and possibly shallow seas. But once the impact slowed, its small size became a disadvantage. Heat escaped quickly. Volcanic activity waned. The magnetic field weakened. The solar wind stripped away much of its atmosphere. Water froze or escaped into space. The landscape dried and cracked. Enormous volcanoes, such as Olympus Mons, and deep canyons, like Valles Marineris, stood as reminders of a more active past. Mars became a quiet, cold desert, its destiny shaped not by violence, but by loss. Beyond the terrestrial planets, the giants underwent transformations of their own. Jupiter's atmosphere developed the banded structure familiar today, alternating belts and zones of swirling clouds driven by internal heat and rapid rotation. Massive storms formed, including the Great Red Spot, which may have begun around this time. Saturn's atmosphere developed similar bands, though more muted. In the cooling era that followed the bombardment, Saturn's early ring structures evolved. Some debris coalesced into moons. Some icy fragments spread into the wide, thin rings we observe now. Uranus and Neptune settled into their distant, cold orbits with atmospheres dominated by hydrogen, helium, and methane. As they cooled, these planets differentiated into layers of exotic ices and superheated water deep beneath their clouds. Neptune, with its internal heat source, showed signs of dynamic weather, including fierce winds, the fastest in the solar system. Uranus, tilted dramatically on its side, displayed seasons so extreme they spanned decades. These distant giants stabilized into worlds defined by cold, pressure, and slow evolution. Moons across the solar system also found their identities. Earth's moon cooled rapidly, forming highlands, Maria, and a surface covered in craters. Jupiter's moons began dividing into categories: Io, volcanic and restless; Europa, icy and smooth; Ganymede and Callisto, layered worlds of rock and ice. Saturn's moons formed as well, with Titan gaining a thick atmosphere of nitrogen and methane. These moons, shaped by cooling and tidal forces, became miniature worlds in their own right. Farther still, the Kuiper Belt solidified into a region of icy bodies orbiting the Sun in a quiet, stable pattern. Objects like Pluto formed distinct surfaces marked by nitrogen ice, methane frost, and slow-moving glaciers. These distant worlds cooled into frozen spheres that would change only gradually across eons. The shaping of the young planets was not only about cooling, it was about stabilization. Each world reached a point where its geological character locked into place. Mercury's crust froze. Venus' atmosphere became permanent. Earth's oceans settled. Mars' climate collapsed. Jupiter's storms matured. Saturn's rings spread. Uranus and Neptune drifted into calm. These identities would remain for billions of years. Though the bombardment had carved deep scars, the era of shaping allowed new features to emerge: mountain ranges, basins, river valleys, lava, plains, ice caps. The solar system was no longer a place defined by fire. It had become a place defined by form. Landscapes took shape. Climate stabilized. Worlds separated into categories: rocky planets inside, giants outside, icy bodies farther still. By the end of this transformative era, the solar system looked familiar. The sun shined steadily. The planets orbited in stable paths. Moons circled their hosts. Belts of debris remained in place. And one planet Earth quietly prepared to take the next step in its story. Once the shaping of the young planet settled and the late heavy bombardment faded into the past, the solar system entered an era of quieter, deeper transformation. The planets were no longer molten spheres or targets of constant impacts. Instead, they began evolving under the influences of geology, climate, atmosphere, and time. Some worlds grew calm and frozen. Others became unpredictable and wild. Earth, in particular, entered a phase of remarkable change, one that would eventually make it unique among all known planets. The first world to stabilize after the bombardment was Mercury. With little internal heat remaining, Mercury's crust became rigid. Volcanic activity slowed to occasional, minor eruptions. Its massive iron core cooled, generating a magnetic field far weaker than Earth's. The surface, already heavily cratered, changed very little over time. With no atmosphere to drive weather or erosion, even the finest dust particles remained largely undisturbed. Mercury became a world defined by stillness. Nothing stirred. Nothing shifted. And across billions of years, its landscape remained one of the most ancient surfaces in the solar system. Venus followed its own extreme path. Volcanic activity persisted far longer than on Mercury, resurfacing vast regions of the planet. Thick clouds of sulfuric acid blanketed the sky, trapping heat and driving temperatures to extraordinary levels. Winds howled across the atmosphere, even though the surface remained eerily calm under crushing pressure. Venus became a world frozen in a perpetual inferno. Though its geology remained active, it evolved in a direction opposite to Earth toward heat, thick atmosphere, and suffocation. By the time the bombardment ended, Venus had already locked itself into this trajectory. Mars, once rich with flowing water and volcanic heat, entered a long decline. As the planet cooled, its magnetic field weakened, leaving the atmosphere exposed to the solar wind. Over millions of years, Mars lost much of its air to space. Lakes evaporated, rivers dried. A world that once could have been wet and temperate slowly transformed into a cold desert. Volcanic activity dwindled, leaving behind towering mountains and deep canyons created during a more active past. Mars became a planet of ghosts, dry riverbeds, ancient lake basins, and frozen polar caps, telling the story of a different era. And then there was Earth, a planet that refused to settle into a simple pattern. As the bombardment faded, Earth's oceans stabilized. The atmosphere cooled. The crust thickened. Tectonic plates drifted and collided, creating the first supercontinents. Volcanic eruptions built new landmasses and enriched the atmosphere with minerals and gases. Earth's magnetic field shielded it from harmful radiation. Heat from the interior drove powerful convection beneath the crust. And slowly, the environment balanced into something rare, a stable climate capable of supporting chemical evolution. Earth's oceans, vast and dynamic, stored heat and moderated temperature. Winds formed weather systems. Rain eroded mountains and transported minerals across continents. Tides shaped coastlines. The moon, steady in its orbit, helped regulate Earth's axial tilt, preventing chaotic swings in climate. Every force worked together to create a planet that was not just stable, but vibrant. During this period, simple organic molecules began interacting in Earth's oceans. Sunlight, volcanic energy, and chemical gradients powered reactions that formed increasingly complex structures. This was not yet life, but it was the foundation for everything that would come. Earth evolved into a laboratory of chemical possibility. Beyond the inner planets, the gas giants continued their slow transformations. Jupiter's atmosphere developed layers of clouds made of ammonia, hydrogen sulfide, and water vapor. Winds intensified, creating bands that wrapped around the planet like swirling ribbons. The Great Red Spot, a colossal storm, deepened and widened. Jupiter's moons evolved as well. Io remained volcanically active, its surface constantly reshaped by eruptions driven by intense tidal forces. Europa's ice crust thickened above a hidden ocean that scientists believe may still exist today. Ganymede and Callisto froze into worlds of ice and rock, marked by cratered surfaces and ancient scars. Saturn, farther from the sun, grew colder and developed its iconic ring system in greater detail. The rings, composed of ice and rock fragments, reflected sunlight and formed a shimmering halo, visible even from great distances. Saturn's moons changed as well. Titan developed a dense atmosphere filled with nitrogen, methane, and complex organic molecules. Enceladus froze on the outside while hiding a subsurface ocean beneath its icy crust. These moons, shaped by chemistry and tidal forces, became some of the most intriguing objects in the solar system. Uranus and Neptune settled into the quiet cold of the outer reaches. Uranus, tilted almost completely on its side, experienced seasons lasting more than 20 years each. Its atmosphere became a pale blue-green sphere of cold, slow-moving clouds. Neptune remained dynamic, its winds among the fastest ever recorded. These two ice giants evolved into worlds defined by distance and temperature stable, quiet, and mysterious. Across the solar system, something remarkable happened during this epoch. Each planet locked into its long-term identity. Differences that began during formation deepened. Mercury became silent. Venus became hot. Earth became dynamic. Mars became cold. Jupiter became stormy. Saturn became ringed. Uranus became tilted. Neptune became windy. These characteristics would endure for billions of years. At the same time, the solar system itself continued to evolve on a broader scale. The asteroid belt stabilized into a region of scattered, rocky bodies. The Kuiper belt solidified into a frozen frontier filled with icy objects. Comets developed long, looping orbits that would occasionally bring them close to the sun. Moons settled into stable paths, and the planets refined their orbits into the patterns we see today. Earth's neighbors continued evolving alongside it. Venus thickened its atmosphere until it became permanently shrouded in clouds. Mars lost most of its water and atmosphere. But Earth's evolution was different. Its climate balanced between heat and cold. Its geological activity reshaped continents. Its oceans remained liquid, and its atmosphere slowly changed composition as physical and chemical processes interacted. This balance created the conditions for something unprecedented in the solar system: life. The first forms of life on Earth were not complex creatures. They were microscopic, ancient, and nearly invisible. But they marked a turning point in the history of the solar system. Life altered Earth's atmosphere, shaping the chemistry of the planet itself. It produced oxygen, created layers of sediment, and sparked a long cascade of biological evolution. No other known planet underwent a transformation quite like this. While life's emergence belongs to another story, its beginnings were intertwined with the era of planetary evolution. The same forces that cooled Earth, shaped its oceans, and moderated its climate also created the environment life needed to appear. One of the most defining features of any planet is its atmosphere. It shapes climate. It protects surfaces. It influences chemistry. And for some worlds, it determines whether life can exist at all. After the chaos of formation and the violence of the late heavy bombardment, the solar system entered a long era in which atmospheres stabilized, thickened, thinned, or vanished entirely. Each world followed a different path, guided by gravity, distance from the sun, geological activity, and time. The result was a set of atmospheres as diverse as the planets themselves. In the early solar system, nearly every rocky world began with what scientists call a primary atmosphere. Light gases like hydrogen and helium captured directly from the protoplanetary disk. But these gases were easily stripped away. Solar radiation, intense heat, and violent impacts caused hydrogen and helium to escape into space. The inner planets lost their primary atmospheres quickly, leaving their surfaces exposed as they cooled. What came next was shaped by internal processes. Each world generated a secondary atmosphere through volcanic outgassing, releasing gases like carbon dioxide, nitrogen, sulfur dioxide, and water vapor from their interiors. These secondary atmospheres evolved dramatically, setting the stage for the very different climates we see today. Mercury, the smallest of the inner planets, never held onto much gas at all. Its weak gravity and proximity to the sun meant that any atmosphere it gained was quickly stripped away. Even outgassed materials escaped faster than they accumulated. Mercury became a world with only a tenuous exosphere, a whisper-thin layer of atoms knocked from its surface by solar wind and micrometeorites. This fragile layer is not a true atmosphere. It cannot trap heat or drive weather. As a result, Mercury became a planet of extremes, where daytime temperatures soared and nighttime temperatures plunged. Venus followed a path that led it toward one of the most dramatic atmospheres in the solar system. Early on, Venus may have had conditions similar to Earth, but as volcanic gases accumulated, they created an atmosphere thick with carbon dioxide. Without oceans to absorb CO2, the gas remained in the sky. Sunlight warmed the planet, and the CO2 trapped heat, intensifying the warming further. This runaway greenhouse effect spiraled until Venus transformed into a furnace. Today, its atmosphere is more than 90 times thicker than Earth's and composed mostly of CO2. Clouds of sulfuric acid reflect sunlight, but the heat remains trapped near the surface. Venus' atmosphere became both its shield and its curse, locking it into a climate no other planet can match. Earth's atmosphere took a more balanced path. After losing its primary gases, Earth built a new atmosphere through volcanic outgassing and chemical reactions in the oceans and crust. Water vapor condensed into rain. CO2 dissolved into oceans and reacted with rocks. Nitrogen, stable and chemically quiet, accumulated over time. The early atmosphere was still harsh, rich in carbon dioxide and ammonia, but Earth's oceans moderated temperature and absorbed greenhouse gases. Life eventually altered the atmosphere further. Microorganisms began producing oxygen, sparking a transformation that reshaped the chemistry of the planet. Over billions of years, Earth developed an atmosphere that could support complex ecosystems. Its balance of nitrogen, oxygen, carbon dioxide, and trace gases became one of the rarest combinations in the solar system. Mars formed an atmosphere through similar processes, but its smaller size meant it could not hold on to gases as effectively. Early Mars had thick air, flowing water, and clouds. But as volcanic activity decreased and its magnetic field weakened, solar wind began stripping the atmosphere away. Over millions of years, Mars lost most of its air. What remains today is a thin atmosphere of carbon dioxide, less than 1% the pressure of Earth's. It provides minimal warmth and almost no protection from radiation. Mars froze not only because it was far from the sun, but because it simply could not keep its air. The outer planets tell a very different story. Jupiter, Saturn, Uranus, and Neptune retained huge amounts of hydrogen and helium, the same gases lost by the inner planets. Their atmospheres became deep, thick, and dominated by lighter compounds. Jupiter's atmosphere developed alternating bands of cloud layers made of ammonia and other chemicals. Giant storms formed, including the colossal Great Red Spot. Saturn's atmosphere remained similar, but with more subtle coloring, its pale bands stretching across a world defined by cold and wind. Uranus and Neptune developed atmospheres rich in methane, giving them their deep blue and aqua tones. Beneath their outer layers, these planets contain exotic mixtures of water, ammonia, and methane under pressures so high they form strange states of matter, superionic ice, and deep oceans of high-pressure fluid. These atmospheres are not thin shells, but deep, complex layers that blend into interiors unlike anything found on rocky planets. Moons across the solar system developed atmospheres of their own. Titan, Saturn's largest moon, formed a thick, nitrogen-rich atmosphere, even denser than Earth's. Methane clouds drifted above hydrocarbon lakes. Titan became the only world besides Earth known to have stable liquids on its surface. Io's thin atmosphere of sulfur dioxide came from volcanic eruptions so intense they reshaped the moon's surface continuously. Triton, Neptune's largest moon, developed a thin nitrogen atmosphere, with geysers spraying icy particles into space. Each atmosphere told the story of its world's past. Some grew thicker, some vanished. Some evolved into complex chemical laboratories. Others froze into silence. One of the most dramatic transitions occurred on Earth. As oxygen levels rose, the atmosphere transformed from one dominated by carbon dioxide and methane into one rich with O2. This change altered climate, drove chemical reactions, and enabled more complex organisms to evolve. Earth's atmosphere became an active participant in shaping its biosphere, something unique among known planets. Atmospheres also influence surface temperatures across the solar system. Venus' thick CO, two-blanket raised temperatures to extreme levels. Mars' thin air allowed heat to escape quickly. Earth's moderate greenhouse effect balanced warmth and cooling. The outer planets, with atmospheres made of hydrogen and helium, held on to internal heat far more effectively than rocky worlds. This internal heat fueled storms, jet streams, and weather patterns that could last centuries. Even the smallest traces of atmosphere mattered. Mercury's exosphere, though thin, revealed how solar wind interacts with surfaces. Pluto's faint nitrogen atmosphere, seasonal and fragile, expands when the dwarf planet approaches the sun and collapses as it moves away. Comets temporarily grow atmospheres of vapor as they heat up, forming glowing comas and long tails. Across every world, the evolution of atmospheres shaped the destiny of the solar system. It determined which planets hosted water, which froze, which burned, and which became laboratories of chemistry. Atmospheres recorded planetary histories, preserved clues, and influenced every geological and biological change that followed. Water is one of the most extraordinary substances in the solar system. It flows, it freezes, it vaporizes, and it shapes landscapes everywhere it appears. It is essential to life as we know it. And yet, water did not begin on Earth. It did not originate in rivers, oceans, or clouds. It came from the earliest days of star formation, long before the planets existed. Chapter 11 explores the story of water, where it came from, how it moved through the solar system, and why it became so important to the evolution of the planets, especially Earth. The origin of water begins in the coldest regions of space. Before the solar system existed, the molecular cloud that eventually collapsed to form the sun was full of simple molecules, mostly hydrogen and helium. But on dust, grains drifting in this cold environment, tiny reactions occurred. Hydrogen atoms combined with oxygen atoms, forming ice that coated the grains in thin layers. These icy grains became part of the collapsing cloud that formed the solar system. As the protoplanetary disk developed, these grains mixed into the material that would soon form planets, asteroids, and comets. But not all water stayed solid. In the inner disk, where temperatures were high, this ancient ice evaporated. Water vapor drifted through the disk, mixing with gas and recondensing only when temperatures fell. In the outer disk, where it remained cold, water stayed frozen, becoming one of the key ingredients in the formation of icy planetesimals. These early, frozen bodies would become the source of much of the water delivered to the planets. The inner planets Mercury, Venus, Earth, and Mars formed in the hot region, inside what scientists call the frost line. Inside this boundary, water could not remain ice. It melted or vaporized, making it difficult for rocky planets to retain large amounts of water during formation. If water existed in these early worlds, it was in the form of vapor, trapped in rock, or absorbed into minerals. But this water was only a fraction of what would eventually arrive. The majority of Earth's water, and perhaps Mars as well, likely came from afar. Comets and icy asteroids formed in the cold outer regions carried enormous amounts of frozen water. When the late heavy bombardment began, these icy travelers were sent inward, crashing into the inner planets. Though destructive, these impacts delivered water in vast quantities. Each collision vaporized ice, creating steam that later condensed into rain. This bombardment filled Earth's early oceans and helped create the conditions necessary for life. But Earth's relationship with water is not just about delivery, it's about cycling. Once Earth cooled enough for water vapor to condense, rain fell for millions of years. Rivers formed, oceans expanded. Water seeped into the crust and circulated through rocks. When volcanic eruptions occurred, water vapor escaped into the atmosphere and rejoined the cycle. Earth became a closed-loop system of evaporation, condensation, and movement. This cycle shaped landscapes, altered climates, and influenced the evolution of life itself. Mars once had a similar cycle, though shorter-lived. Deep valleys carved by ancient rivers indicate a time when water flowed freely across its surface. Lakes pooled in craters. Perhaps even shallow seas spread across portions of the planet. But as Mars lost its atmosphere, its water either evaporated into space or froze beneath the surface. Today, Mars holds enormous amounts of water ice in its polar caps and hidden underground, locked away in a frozen state but still present. Venus, on the other hand, took a different path. If Venus once had water, and many scientists believe it did, it lost it long before the present day. Rising temperatures caused water vapor to accumulate in the atmosphere. Sunlight broke the molecules apart, and hydrogen escaped into space. Venus lost the ingredient Earth relied upon for habitability. Without water, Venus became a furnace of carbon dioxide and sulfuric acid. Mercury, too small and close to the sun, never had much water to begin with. Yet surprisingly, ice still exists in permanently shadowed craters near its poles, where temperatures remain far below freezing. These icy deposits likely came from comets and asteroids long after Mercury cooled. They remain frozen today because sunlight never reaches the deepest parts of these craters. Beyond the inner planets, water is far from rare. In fact, the outer solar system contains vastly more water than Earth. Jupiter's moon Europa hides a global ocean beneath its icy shell, kept liquid by tidal heating. Saturn's moon Enceladus contains a subsurface ocean as well, with geysers blasting water vapor into space. Titan has lakes not of water, but of methane and ethane, yet it still contains vast amounts of frozen water in its crust. Ganymede, Callisto, and Triton all contain ice and may hold oceans beneath their surfaces. Even farther out, the Kuiper Belt is full of water-rich objects, icy bodies like Pluto and Eris that formed in the coldest parts of the disk. These distant worlds hold ancient water that has remained frozen for billions of years, preserving the chemical fingerprints of the early solar system. Water's movement through the solar system didn't just shape planets. It shaped possibilities. On Earth, water enabled chemical reactions that led to the first forms of life. In underground oceans on distant moons, water may create environments where life could exist today, even on Mars. Frozen water preserves clues about a time when the planet was warmer and more active. The cycling of water, its ability to shift between solid, liquid, and vapor makes it uniquely powerful. It sculpts landscapes, erodes mountains, fills basins, and forms glaciers. It moderates temperature. It dissolves minerals, carries nutrients, and supports biological processes. Among all substances found in the solar system, water is the only one capable of shaping a world so thoroughly and so deeply. Earth's oceans, in particular, became engines of climate and chemistry. They influenced weather patterns, absorbed carbon dioxide, and created stable habitats that allowed life to flourish. Without water, Earth would be a silent, barren world. With it, the planet became something entirely different, dynamic, evolving, alive. Moons are more than just companions to planets. They are sculptors of tides, stabilizers of rotation, engines of geological activity, and archives of ancient impacts. In the story of our solar system, moons play roles nearly as important as the planets themselves. Some shaped the evolution of their host worlds. Others developed complex personalities of their own. And all of them formed from the same swirling cloud of dust and gas that gave rise to everything else. The formation of moons began early, during the era of collisions and cooling. Each planet built its own system, shaped by location, timing, and chance. Some moons formed from leftover material that never became planets. Some formed from impacts. Others were captured foreign bodies pulled into orbit by gravity. And each type of moon told a different story. Earth's moon is perhaps the most well-known, and its origin is among the most dramatic. Around 4-5 billion years ago, a Mars-sized body, Theia, collided with the young Earth. The impact was so violent it melted both worlds and ejected enormous amounts of debris into orbit. Over time, that debris merged into a single body, our moon. This origin gave the moon a unique composition and a strong gravitational connection to Earth. It also created one of the most important relationships in the solar system. The moon stabilized Earth's rotation. Without it, Earth would wobble unpredictably, causing chaotic climate swings. But with the moon, Earth's tilt remained steady. Seasons became predictable. Climate stayed balanced. The moon also generated tides that shaped coastlines, stirred oceans, and may have played a role in the early chemistry that led to life. Even today, the tug of lunar gravity slows Earth's rotation gradually, altering the rhythm of days and nights over geological time. Mars developed two moons, Phobos and Deimos, tiny, irregular worlds that appear more like captured asteroids than formed satellites. Their strange shapes and cratered surfaces tell the story of their origins. They were likely once part of the asteroid belt, nudged into Mars' gravitational reach and trapped in orbit. Phobos is slowly spiraling inward and may one day break apart, forming a brief ring around Mars. Deimos, farther out, drifts slowly away. Though small, these moons played a role in shaping Mars' tides and recording its impact history. The gas giants, with their immense gravity, developed moon systems that resembled miniature solar systems of their own. Jupiter's moons, Io, Europa, Ganymede, and Callisto became four of the most fascinating worlds in the solar system. Io, the innermost, is a world of fire. Its orbit places it under extreme tidal forces from Jupiter and nearby moons, stretching and heating its interior until it becomes the most volcanically active body known. Molten rock erupts across its surface, reshaping it constantly. Europa, slightly farther out, experiences tidal forces strong enough to flex its icy surface. This flexing generates heat, melting the interior ice and maintaining a global ocean beneath its crust. Europa's hidden ocean is one of the most promising locations for extraterrestrial life. Ganymede, the largest moon in the solar system, possesses its own magnetic field and likely contains a layered structure of oceans and ice. Callisto, ancient and heavily cratered, preserves a record of impacts stretching back billions of years. Saturn developed its own family of moons, each different, each remarkable. Titan, the second largest moon in the solar system, formed a thick atmosphere rich in nitrogen and methane. Lakes of liquid hydrocarbons formed on its surface, creating a chemistry unlike anything on Earth. Titan's atmosphere is a window into the early conditions of planets. Enceladus, another Saturnian moon, hides a subsurface ocean beneath a crust of ice. Geysers of water vapor erupt from fractures in its surface, spraying icy particles into space and feeding Saturn's rings. Enceladus Ocean, warmed by tidal heating, may host chemical reactions similar to those that once occurred in Earth's oceans. Uranus moons formed from the debris left after the planet experienced a dramatic tilt, likely caused by a massive ancient impact. These moons, such as Miranda, Ariel, and Titania, display unusual geological features, cliffs, canyons, and resurfaced plains created by internal heating early in their history. Neptune's largest moon, Triton, was captured, not formed. Once a dwarf planet from the Kuiper Belt, Triton was pulled into Neptune's orbit and transformed by tidal heating. Its surface shows signs of cryovolcanism, eruptions of ice rather than molten rock. Across the solar system, tidal forces shaped moons and planets alike. Tidal forces arise when gravity pulls one side of a world more strongly than the other. This stretching generates friction and heat, influencing geology. On Earth, tides drive ocean currents and influence weather patterns. On Io and Enceladus, tides power volcanic and cryovolcanic activity. On Europa, tides maintain a liquid ocean beneath ice. Tides are quiet but powerful, shaping worlds from the inside out. Moons also influenced rotation and stability. Earth's moon slowed the planet's rotation from a fast 6-hour day to the 24-hour cycle we know today. The moons of Jupiter and Saturn fell into resonant orbits, mathematical relationships that maintain stability and amplify tidal effects. Triton's retrograde orbit slowed Neptune's rotation over time. The gravitational interplay between moons, planets, and the sun set up a complex dance that has lasted billions of years. Moons captured debris long after the bombardment ended, recording impacts that planets erased. Their surfaces preserve ancient histories. Craters reveal when collisions were common. Smooth plains hint at volcanic resurfacing. Ridges and fractures tell the story of cooling and stress. Many moons act like geological notebooks from eras long gone. Some moons, especially those around the gas giants, may hold environments warm enough for life not on their surfaces, but in the hidden oceans beneath their crusts. The combination of liquid water, chemical energy, and tidal heating makes these moons some of the most intriguing objects in the solar system. As the solar system evolved, moons became essential partners to planets. They shaped tides, influenced climates, recorded impacts, and created geological wonders. Without moons, many planets would look very different. Earth might be unstable, Mars might lack its faint seasonal variations. Jupiter's system would miss entire worlds of fire and ice. Saturn's rings would be sparse or non-existent. Beyond Neptune, far past the orbit of the last major planet, lies a region of the solar system that feels almost untouched by time. It is cold, dark, and quiet, so distant from the sun that light itself arrives weakened, like a faint whisper. This vast frontier contains the oldest, most primitive objects in the solar system, frozen relics left behind from the era of planet formation. Together, they form two distinct structures, the Kuiper Belt and the Oort cloud. Chapter 13 explores these frozen regions, how they formed, and why they hold some of the most important clues to the solar system's origin. The Kuiper Belt begins just beyond Neptune's orbit, roughly 30 astronomical units from the Sun. It stretches outward like a broad, flat ring of icy bodies, remnants of the protoplanetary disk that never merged into planets. Temperatures here are so low that water, methane, nitrogen, and carbon dioxide remain frozen solid. The Sun is a distant point of light, providing little warmth. Yet, in this cold frontier, thousands of icy objects orbit silently, small, dark worlds that preserve their original chemistry. The Kuiper Belt formed during the earliest stages of the solar system. As the giant planets migrated to their present positions, their gravity reshaped the disk. Jupiter scattered countless icy planetesimals, sending some inward and others outward. Neptune, moving slowly outward, pushed material ahead of it, carving the Kuiper Belt into a region of stable orbits. Much of the mass that once existed here was lost during this chaotic time, but what remained became the icy bodies we see today. These objects range from tiny fragments only a few kilometers across to dwarf planets hundreds or even thousands of kilometers wide. Pluto, once considered the 9th planet, is the most famous of them. With its thin atmosphere, nitrogen, ice plains, and mountains of water ice, Pluto is a complex, dynamic world. Its companion Charon, nearly half its size, forms a binary system unlike anything else in the inner solar system. Other Kuiper Belt objects, such as Haumea and Makemake, are equally intriguing elongated shapes, unusual spin rates, and bright icy surfaces hint at violent histories. Many Kuiper Belt objects are locked in resonances with Neptune. This means their orbital periods follow mathematical ratios with Neptune's orbit, preventing collisions and maintaining long-term stability. These resonances form during the migration of the giant planets, capturing icy bodies and freezing them into predictable paths. The Kuiper Belt, though distant and icy, is not random. It is structured by gravity and shaped by billions of years of subtle interactions. But the Kuiper Belt is only the beginning of the solar system's frozen frontier. Far beyond it, stretching almost halfway to the nearest stars, lies the Oort cloud, a vast, spherical shell of icy bodies that surrounds the solar system like a ghostly halo. Unlike the Kuiper Belt, which lies mostly in a flat plain, the Oort cloud exists in all directions. It forms the outermost edge of the Sun's gravitational reach. The Oort cloud is so distant that no spacecraft has ever approached it. Even our most advanced telescopes cannot directly observe its objects. Yet its existence is revealed through the behavior of long-period comets, icy wanderers that arrive from the far reaches of the solar system. These comets follow elongated orbits that take them thousands of astronomical units from the Sun. Their movements suggest they originate from a region so distant that sunlight barely touches it. The Oort cloud likely formed during the violent early days of the solar system. As Jupiter, Saturn, Uranus, and Neptune migrated, their gravity flung countless icy planetesimals outward. Some were ejected into interstellar space entirely. Others were trapped in distant orbits by the sun's gravity. Over millions of years, interactions with passing stars and galactic tides nudged these orbits into a spherical distribution, creating the vast cloud we infer today. The Oort cloud contains perhaps trillions of icy objects, though each is separated by immense distances. If you stood on one of these objects, the nearest neighbor might be millions of miles away. It is a region of silence so complete that nothing changes on human timescales. Even on geological timescales, Oort cloud objects evolve slowly, orbiting the sun over periods so long that billions of years may pass before a comet completes a single revolution. Despite their distance, the icy bodies of the Oort cloud sometimes find their way into the inner solar system. A passing star, a galactic wave, or even subtle gravitational interactions can nudge their orbits, sending them inward. These events are rare, but when they occur, long-period comets streak toward the sun, their icy surfaces vaporizing and forming brilliant tails. These comets are messengers from the frozen frontier, carrying ancient material preserved since the birth of the solar system. The Kuiper Belt and Oort cloud hold immense scientific importance. They contain some of the most pristine material left from the early solar system. Unlike planets, which underwent heating, differentiation, and geological evolution, these icy bodies remained largely untouched. Studying them reveals the original composition of the protoplanetary disk, the chemistry of the early solar environment, and the processes that dominated during planet formation. These regions also shape the history of the inner solar system. Comets from the Kuiper Belt and Oort cloud delivered water and organic molecules to Earth billions of years ago. They stirred the atmosphere, influenced climate cycles, and seeded the young planet with materials that contributed to life's beginnings. Even today, comets occasionally bring new organic compounds into Earth's atmosphere, continuing a slow cosmic exchange that began billions of years ago. The Kuiper Belt also helps us understand the architecture of planetary systems beyond our own. Many distant star systems show evidence of debris disks regions similar to our Kuiper Belt. Studying the structure of our own frozen frontier helps astronomers decode the evolution of other planetary systems, revealing how common or rare planetary architectures like ours truly are. The Oort cloud, on the other hand, reminds us of the solar system's connection to the galaxy. Its formation was influenced not only by the sun and planets, but by passing stars and galactic tides. It represents the boundary between the solar system and interstellar space, a region where the sun's gravity competes with the pull of the Milky Way itself. The Oort cloud is the solar system's frontier, its edge, its shield, and its ancient archive. By the time the planets cooled, the bombardment ended, and the distant icy regions settled into place. The solar system had transformed from a swirling cloud of gas and dust into a structured, harmonious system. The arrangement we see today, rocky planets on the inside, giants in the middle, and icy bodies on the outskirts, did not arise by accident. It emerged from billions of years of gravitational interactions, migrations, collisions, and cosmic chance. Chapter 14 explores the grand architecture of the solar system, how it came to be, and what it reveals about our cosmic origins. The solar system is not just a collection of planets orbiting a star. It is a dynamic system with layers, each shaped by temperature, chemistry, and motion. The innermost region is defined by heat. Here, only metals and silicate rocks can survive near the blazing sun. This is why Mercury, Venus, Earth, and Mars are small, dense, and rocky. Their formation was limited by the materials that could withstand intense radiation and by the gravitational influence of nearby giants. Beyond the terrestrial planets lies the asteroid belt, a vast region filled with rocky bodies but lacking the mass to form a full-sized planet. This area is sometimes called a failed planet, but in reality, it reflects the powerful role Jupiter played in shaping the solar system's structure. Jupiter's gravity disrupted the region so strongly that material could not coalesce into a stable world. Instead, the belt became a collection of leftovers from the early days of planet formation. Some of its objects are ancient and primitive, untouched since the dawn of the solar system. Others have undergone heating, fracturing, or even differentiation. Farther out lie the gas giants, the planets that define the middle region of the solar system. Jupiter, Saturn, Uranus, and Neptune are not only massive, they are spaced in a way that reflects the conditions of the protoplanetary disk and the migration that occurred early in the system's history. Jupiter formed first, carving a path through the disk and redirecting material inward and outward. Saturn followed, interacting with Jupiter's orbit in a gravitational dance that affected the entire solar system. Their combined resonance altered the distribution of planetesimals, shaped the asteroid belt, and sent icy bodies into the outer regions. Uranus and Neptune, forming in colder regions, grew into ice giants, acquiring thick atmospheres of hydrogen, helium, and methane. Their migration outward helped create the Kuiper Belt, pushing icy objects into stable orbits beyond Neptune. The spacing between the giant planets is not random. It reflects a delicate balance of gravitational forces, orbital resonances, and the dissipating protoplanetary disk. Beyond Neptune lies the Kuiper Belt, a broad, flat zone of icy bodies that stretches outward for billions of miles. This region marks the transition from the inner solar system to the deep frontier. Objects here orbit slowly, influenced by the faint pull of the Sun and the distant tug of Neptune. The Kuiper Belt is the source of many short-period comets and contains dwarf planets like Pluto, Haumea, and make worlds that reveal the diversity of planetary building blocks. Farther still lies the Oort cloud, the spherical shell of icy bodies that surrounds the solar system at its greatest reaches. This distant frontier represents the outermost layer of the Sun's gravitational influence. Its existence reflects the chaotic early days of planetary migration and the interactions between the solar system and passing stars. The Oort cloud contains material left over from the earliest stages of formation, preserved in near-perfect condition. Taken together, these regions form a layered structure: terrestrial worlds, remnants of formation, giant planets, icy belts, and a frozen halo. Each layer reflects the interplay of heat, gravity, chemistry, and time. The solar system's architecture holds clues about how planets form not only here, but around other stars as well. Patterns emerge when we examine this architecture closely. One pattern is the radial temperature gradient. Near the Sun, heat keeps only metals and rock intact. Farther out, ices and gases remain stable. This is why rocky planets form inside and giants form outside. Temperature, one of the simplest physical conditions, set the stage for the entire layout. Another pattern is orbital resonance. Many objects are locked into rhythmic orbital relationships that prevent collisions and create long-term stability. Jupiter and Saturn's orbits have played an enormous role in shaping the distribution of asteroids, comets, and even the spacing of other planets. Resonances in the Kuiper belt protect objects from Neptune's gravitational influence. These orbital rhythms, like the beats of a cosmic drum, keep the solar system stable. A third pattern is migration. The planets did not always occupy their current orbits. Jupiter likely moved inward and then outward. Saturn moved outward. Uranus and Neptune migrated significantly, reshaping the outer disk. This migration created gaps, belts, and resonances that remain to this day. The present architecture is the result of motion and change, not static formation. A fourth pattern is the division of chemical zones. Each region of the solar system contains a unique mixture of elements and compounds. The inner planets contain iron, nickel, and silicate rocks. The gas giants contain hydrogen and helium. The ice giants contain methane, ammonia, and water in various forms. The Kuiper belt contains nitrogen and methane ices. The Oort cloud contains pristine fragments left from the primordial cloud. Chemistry follows distance, and distance follows heat. Architecture is not only about structure, it's also about function. The arrangement of planets helped stabilize the solar system over billions of years. Jupiter's gravity reduces the number of dangerous comets that reach the inner worlds. The asteroid belt provides a reservoir of material for scientific study. The Kuiper belt preserves the solar system's early history, and Earth's position far enough from the sun to avoid scorching, close enough to avoid freezing, created the rare conditions that allowed life to flourish. One of the most fascinating aspects of the solar system's architecture is how common it may be. Observations of exoplanetary systems reveal similar patterns: hot inner terrestrial planets, outer gas giants, and distant debris belts. Some systems contain hot Jupiters, giant planets orbiting extremely close to their stars. Others show evidence of migration, resonance, and layered structures. Our solar system is not an anomaly. It is one example of a broader cosmic pattern shaped by universal laws of physics. And yet, every system is unique. The precise arrangement of worlds around our sun, the balance of masses and distances, the timing of migrations, and the chemical distribution all combined to produce a system capable of hosting life. Change any of these elements, and Earth may never have formed in its current state. Jupiter's orbit, the thickness of Earth's crust, the delivery of water, the presence of the moon each became a critical component in a delicate architecture. The solar system we know today is stable, familiar, and predictable. The planets move in smooth orbits. The sun shines with steady light. Moons follow ancient paths. Comets occasionally sweep inward from the frozen frontier, but nothing disrupts the overall harmony. Yet, like every story in the universe, this one has a beginning, a middle, and eventually an end. To understand the full arc of our solar system, we must look ahead far into the distant future, across spans of time so long they stretch beyond human imagination. In the short term, over the next few million years, very little will change. Earth will continue to rotate more slowly as the moon drifts gradually outward. The continents will move, merge, and break apart again. Jupiter's storms will shift. Saturn's rings may evolve or thin. Comets will arrive from the Kuiper belt and Oort cloud. But most of the system will remain as it is, with planets following the same stable orbits they have traced for billions of years. Over the next 100 million years, more gradual changes accumulate. Saturn's rings, made of ice and dust, will either spread out or fade as material falls toward the planet, or escapes into space. Mars moons will shift. Phobos will eventually cross the point where tidal forces tear it apart. When that moment arrives, Phobos may break into fragments that form a temporary ring around Mars, an echo of the rings we see around Saturn today. As hundreds of millions of years pass, the sun's brightness will slowly increase. The sun is a main sequence star, which means it shines steadily while fusing hydrogen into helium in its core. But as the sun ages, its core composition changes. Helium builds up, pressure rises, the outer layers warm. This warming will cause Earth's climate to shift. Oceans will gradually evaporate. Weather patterns will change. Over hundreds of millions of years, Earth will become warmer, losing the ability to support complex life. Farther out, planets like Mars might briefly become more temperate. As Earth heats, Mars could experience a slight rise in temperature, though likely not enough to produce stable liquid water. Jupiter's moons might also warm slightly, but not enough to transform their deep frozen surfaces. 1 billion years from now, Earth's oceans may begin to disappear. The atmosphere will thicken with water vapor, which traps even more heat. A runaway greenhouse effect, similar to what occurred on Venus, could unfold. Earth, once vibrant and full of life, could become a world of intense heat and empty, cracked land. Life, if it survives at all, will persist only in the deepest oceans, hidden underground, or in microscopic forms adapted to extreme conditions. As the sun ages further, it moves slowly toward the end of its main sequence life. Approximately 5 billion years from now, the sun will run low on hydrogen fuel. Its core will contract. Temperatures inside the sun will rise dramatically. The outer layers will swell outward. The sun will transform into a red giant, a massive, glowing sphere that extends far beyond its current size. When this transformation begins, Mercury and Venus will be the first to face destruction. The sun's expanding outer layers will engulf Mercury completely. Venus will likely be consumed shortly after. Earth's fate is more uncertain. Some models suggest the sun's expansion will swallow Earth. Others propose that, as the sun loses mass, Earth's orbit may shift outward just enough to escape total destruction. Even in the best case, Earth will be scorched. Its surface will melt. Its atmosphere will be stripped away. The planet will no longer resemble the world we know. Mars, farther out, may survive the expansion phase, but will experience intense heating. Surface ice will vaporize. The skies will glow red as dust storms swirl through the thinning atmosphere. Worlds that once seemed frozen and quiet will be thrust into dramatic, temporary change. The outer planets, Jupiter, Saturn, Uranus, and Neptune will remain intact, though the sun's transformation will alter their environments. As the sun loses mass, their orbits will expand. The icy worlds of the outer solar system may warm slightly, though not enough to become habitable in the long term. The Kuiper belt will drift outward as well. The Oort cloud, barely bound to the sun even now, may loosen, releasing objects into interstellar space. As the sun reaches its red giant peak, it will lose enormous amounts of mass through stellar winds. These winds will strip material from the outer layers and carry dust and gas into space. After millions of years of expansion, instability, and pulsing changes, the sun will shed its outer layers entirely. What remains will drift outward, forming a glowing planetary nebula, a beautiful, expanding shell of gas illuminated by the dying star within. At the center of this nebula will be the Sun's final form, a white dwarf. Small, dense, and incredibly hot, the white dwarf will contain most of the Sun's original mass, but compressed into a body about the size of Earth. It will no longer fuse hydrogen or helium. Instead, it will slowly cool over billions of years, fading toward darkness. What remains of the solar system at this stage will be unrecognizable. The inner planets will be gone. The outer planets will orbit farther out than before. Moons will drift or break apart. The asteroid belt and Kuiper belt will thin. The Oort cloud will fade. And yet, the solar system will endure a ghost of its former self, quiet and slowly dimming. On timescales far beyond this, measured in trillions of years, the white dwarf may cool into a black dwarf, an object so cold and dark it emits virtually no light. The planets that remain will continue orbiting for unimaginable stretches of time, unless gravitational encounters with passing stars eventually eject them into interstellar space. And yet, even in this distant future, the story of the solar system does not feel tragic. Rather, it is the natural arc of all systems, born from collapsing clouds of gas and dust. Stars ignite, planets form, worlds evolve, life may arise. Then, over billions of years, everything transforms again. The solar system is not a fixed place. It is a living system shaped by time. The story that began with a collapsing molecular cloud billions of years ago will end in the quiet fading of a white dwarf. But in between, it gave rise to planets full of wonder, to moons of fire and ice, to comets carrying ancient ingredients, to oceans, mountains, storms, and landscapes shaped by forces vast and subtle. And on one small world, orbiting at just the right distance, it allowed life to appear, to learn, to wonder, to look up into the sky and question its own origins. As you drift toward sleep, let your mind settle back into the quiet beginning of everything. Imagine the soft glow of the newborn sun, warming the dust of the ancient cosmic cloud. Imagine planets forming slowly, peacefully, each one finding its place in the dark. The chaos has faded now. The fire has cooled. The collisions have passed. All that remains is the rhythm of orbits, steady, calm, eternal. Breathe in gently and picture the vastness of space stretching around you, silent, endless, comforting. Breathe out slowly and let the weight of the day dissolve into stardust. You are floating through a peaceful universe where time slows, where light softens, where everything moves in quiet harmony. Feel yourself drifting, gently, like an ancient grain of dust carried by the currents of a warm cosmic breeze. Every star you've ever seen began in a moment just like this: stillness, darkness, and a spark waiting to be born. Tonight, let that spark guide you into rest. Let the story of our solar system cradle you. The sun shining softly, the planets circling in silence, the distant hum of the cosmos holding you safe. You are part of this universe made of its atoms, shaped by its time, carried by its light. And now, you can let go. Close your eyes. Breathe deeply. Feel the calm of the cosmic night surround you. The solar system is at peace. And so are you. Good night.